Okay, so in lecture 6, we are going to learn about some practical issues of training neural networks. So this will be covered in today's lecture and the next lecture, in lecture 7. So where we are, so you may remember these slides in lecture 3, as far as you remember. Machine learning is a data-driven approach. So we, human, just design the form of our model, and we initialize the parameter values randomly at the beginning. And then we feed the training data, which is paired of x and the label, the ground truth label, y hat. Just y. And we estimate the label, which is called y hat, and we compare the difference between them, which is we call loss function. And then we update the parameters w based on those laws. And we repeat this until we have correct prediction for most of those examples. This is the general framework of the machine learning. And I think I have mentioned that we have one example of all of these things, and we are going to focus on how to design these models in the rest of this course. But before we move on to that, there are actually a lot of options in many parts in these slides. For example, if we design a neural networks, we have seen just a few activation functions, but which one we should use for our data? Or when you initialize the hyperparameter values randomly, but is it okay to be just fully random, or is there anything that we need to take care? And for the training data, do we just use the raw data as it is, or do we have to do some pre-processing or anything to improve the performance of our model? And when you update the parameters of the model, we learned about the stochastic gradient descent, which we compute the gradients using some examples and then updates towards the direction of the gradients. But how much we have to update, which we call learning rates. How can we decide that? And we just said that we are going to repeat until we have good performance. But what does that mean? And when should we stop? Or how to regularize the training overall? So all of these nitty-gritties are actually affecting the performance of our models significantly. So you have to know some practical things like this to actually train your model efficiently and effectively. Even though you have very nice model, if all of these things are not properly treated, you're not going to get a good results in your experiments. So actually, these things will be important when you do your homeworks in this course and when you do your research for your thesis and for your entire career. So I would like to emphasize the importance of this practical stuff. So today in the next lecture, we are going to see some details of these nitty-gritties. First, let's start with activation functions. In previous lecture, we have learned some activation functions like this. Sigmoid function or tangent h, hyperbolic tangent function, or ReLU. We just have seen these pictures, but we didn't really discuss what's the pros and cons of these. So which one we should use? The first option is the sigmoid function. So in the previous lecture, we mentioned that the output of this function is very nicely ranged between 0 and 1. So we can easily apply this to interpret it as a probability. Historically, the sigmoid was the only choice or the main choice for neural networks. And that was actually working quite nicely because we have very small data and we used only very shallow, small model. But unfortunately, sigmoid function turns out to be not a good choice for modern deep neural networks. There are three reasons here in the order of importance. The first reason is that the neurons will be saturated by killing the gradients. We are going to discuss more details in the next slides. And the second reason is that this one outputs only positive numbers, which is not a good thing. And also, exponential function here is computationally expensive, this is minor, but the first two things are really important reason not to use sigmoid function. So let's see one by one. Sigmoid function looks like this, and probably you may remember when you take the gradients of this function with regard to its input, it's given like that. You have to practice this by just taking the actual gradients with this, but yeah, this is the result of the taking the gradients here. So let's see. What is the gradient when x is 10? 10 is some large number here. So suppose 10 is here. So what is the gradient when x is 10? E to the minus 10 is almost 0, right? So it's 1, 1. So that means when you take the gradients, this one will be almost 1, which means this part will be almost 0. So it's, when you multiply these two, the gradient will be almost 0. And actually, you can see that in this graph as well. The gradients of this function around here seems like almost 0. You can actually check that from the graph and from the equation. What about x is minus 10? Here, e to the minus 10 is e to the 10, which is very large number. So this will be almost 0. So same thing happens. 0 times 1 is still 0. And the gradient here is almost 0. Which means if the input is in large magnitude, regardless of its sign, the gradient will be 0. The gradient of this function with regard to its input is like that. So if input is large enough, then actually the gradient will be almost 0. Why does that matter? We use this gradient to update the value of the parameters, right? So for this node, we have some input and we have the output like that. This is the forward pass. And when you compute the gradients, from this upstream gradients, what we do is computing the local gradients within this node, and we output multiplied with the upstream gradients. So whatever we have received here as the upstream gradients, the local gradients will be 0 if the input is large. But it's not extremely large. If it's just like 5 or even like 3 or 5, then the gradient is almost 0. And because we have too many layers are stacked to each other, whenever we have passed just one sigmoid, it will be multiplied with very small number, like 0.001. And once we pass that like 3 times or 5 times, it will be converging to 0. So we actually learn nothing at the earlier stage of the neural networks. So this is the most significant problem with the sigmoid function when you train the model. And the second problem is the sigmoid function outputs only positive numbers. So why that is a problem? Consider what happens when the input is always positive, which actually happens a lot in practice. Suppose our example, we are doing computer vision, and what is the input of the computer vision model? It's an image, right? And remember, what was the image? It was a sequence of bunch of numbers, which is integer between 0 and 255, which is the pixel intensity. So all positive. So computer vision is a good example of this case. All the inputs are positive, and this sigmoid function always outputs a positive numbers. So again, we have some linear transformation of the input, and we take the sigmoid function on top of that. Then we compute the gradients, upstream gradients and local gradients, and we multiply them. See here, when the sigmoid function is taken with partial derivative with each element of the weights, it looks like this. Remember that the sigmoid function's derivative is itself times 1 minus itself. And because we have this linear transformation, xi came out when we take the partial derivative with wi, because wi and xi are multiplied to each other. Here, this part is always positive. Remember, sigmoid function outputs between 0 and 1. So this can't be negative, always positive. And we assume that this input is always positive here, like pixel values. So this means this gradient is always positive for all of these i's. Why does that become a problem? The sigmoid node does not change the sign of the upstream gradients for all wi, not just one. Because this is a vector, we are going to take the partial derivatives with these wi's for all the i's in this vector, but that will be all positive, which means depending on the input, all the gradient elements are either all positive or all negatives, which means the gradient updates can go only to particular directions. So here's a simple example. Suppose that the correct direction of the gradient is this way, which is the x1 is to the right, which is to the positive, but x2 is going to the down, which is negative. So one of them should be positive, one of them should be negative. But such a case, using if we use the sigmoid function, the gradient should be always to the same direction, which is negative to the negative, negative and negative, which is to the left downwards, or to the right and upwards. It does not allow some directions like this, to the right and to the bottom. Are you following? This is a little bit complicated. So the gradient, gradient is a vector because the input is vector, and each of those elements always have the same sign if we use the sigmoid function because of this property, which means if the gradients need to be in a mixture of different signs, like this situation, it's very, very, very inefficient. It takes like zigzag like that. But in practice, this problem is less severe because we usually use the mini batch. So we take the multiple examples of the gradients and we take the average of that to updates. So this actually does not really happen when you use some mini batch of size like of 64 or something larger than that. So this is less severe than the previous problem, but this still causes some problem because we have to always have the same sign or direction of the gradient updates, which is really inefficient. For these reasons, sigmoid function is no longer used in practice except for when we really need the probabilistic interpretation at the end of the very end of our classification layer. So what else we have? Someone raise a hand. Junbom?
Yeah, Professor, I have a question about the last slide. So I can understand that we have all the positive number because you explained the equation in the left bottom part. But I'm curious about why it became all negative, because it seems that its result is always positive. So can you explain why it can be all negative?
So here, the local gradient is always positive, but we don't have any assumption about the upstream gradients. So if it was a negative, then it doesn't change its sign. It's still all negative.
Okay. Yes, thank you.
So other than the sigmoid function, what other options we have? So people gave some ideas like this, which is the hyperbolic tangent function. So it looks like this, and now it outputs between -1 to 1 rather than 0 to 1. So the output is zero-centered, and we have both positive and negative out of this function, which is great. But still, the killing gradients happens, which is the most serious problem with sigmoid. And indeed, this tangent h function is just scaled version of the sigmoid function. So we are not still overcoming that problem. You see that with the large inputs, like 10 or -10s, we have gradients of almost 0. So with the emergence of deep learning, deep neural networks, people considered what other non-linearity function we should use as the activation function. And this is actually one of the most widely used ReLU, or rectified linear units. So it's very simple function like that. If the input is positive, we just output it as is. If it's negative, we just output 0. So when we have any negative numbers, we just delete that, and that's it. So this function looks like this. And here are the reasons we have to use this. It does not saturate in the plus region, which means whatever the large numbers we are given, the gradient will be still the same, always 1. So even for very large inputs like that, we don't have the diminishing gradients problem with this. And it's computationally very efficient because you just check its sign. And if it's positive, the gradient is always 1. If it's negative, the gradient is always 0. So you don't have to compute the actual derivative of those complex functions. So for that reason, this converges much faster than sigmoid or hyperbolic tangent function in practice. But this one has its own problem too. First of all, this one does not output zero-centered. This is always non-negative, the same issue with the sigmoid function. And as you may already figured out, this function is not differentiable at this point when x is 0. Interestingly, this is not really significant because you can just use any subgradient here. It's between 0 and 1, or you may just use whatever number between 0 and 1. And then in practice, actually, it learns OK. So this is not really significant, fortunately. But this one is another issue, dead value problem. If the initial input is negative, then the gradient will be 0 and learns nothing. What happens next? It doesn't change any weights on that node. So in the next one, it will output the negative again. So it will not be updated again. So if the initial output of some node is negative, then that node will never be updated because of this the characteristic of this function. So if you use ReLU, usually we initialize the value with slightly positive biases. Otherwise, it will be dead at the beginning, and you are not going to use that node at all. So to overcome these drawbacks of ReLU, some people have designed some slight change of these values. One of them is called leaky ReLU. So instead of having 0 in the negative region, we have some small slope, like 0.1 or 0.01, like this. And we still have some something to learn in the negative region. So now it does not saturate in all regions. We always have the constant gradients, both in positive and negative regions. And this is computationally efficient because, as I said, in the positive region, we have the gradient is always 1. In the negative region, this 0.01 here. And for that reason, it still converges much faster. And no dead value problem here, because even if it starts with some negative outputs, still we can update because the gradient is not 0 here. Where there's almost this is okay. I said this is reason not to use, but it's not really serious. One drawback of this approach is we have to decide what this slope should be, which is called, yeah, I don't have the name here, but slope, where x is negative. So leaky ReLU is quite a good choice for most neural networks, overcoming the drawbacks of the value. And ELU, exponential linear unit, is another, or LU, is another activation function you can use instead of the pure ReLU. So this one contains all the benefits of the ReLU, but also we have some exponential function in the negative region. So it's not going to the infinite like that, but it actually converges here. So negative saturation regime compared to leaky ReLU, it's a little bit more robust. And it's closer to the zero mean outputs. In this case, it's not zero mean. This side is much larger, but it tries to make this a little bit more zero mean outputs. But this one has another drawback, which is exponential function is a little bit computationally expensive, but that's not really a big deal. So LU is also another good choice to overcome the drawbacks of the ReLU. But in practice, you can actually just forget about those things when the ReLU is the pure ReLU is the default choice for most of the neural networks. But you have to be careful with the initialization and the learning rates when you use ReLU. And once you have a good network, and if you'd like to improve it a little bit, then you may try this leaky ReLU or LU to squeeze out some marginal gains. But actually, you can try this pure ReLU, vanilla ReLU for your networks in most cases. But this is most important. Do not use sigmoid or hyperbolic tangents. These are not really efficient, and it's rarely used in modern neural networks. So yeah, we have talked about the activation functions, and let's move on to data preprocessing. So if we have infinite amount of data, okay, we have one question from Wichan, Ko Wichan.
Professor, do you hear me?
Yeah.
I'm sorry for not showing my face due to my technical problem.
Okay.
So we are learning all these activation functions for they can allow nonlinearity. And my question is that is there any difference among the activation functions with regard to the degree of
Degree of what? Sorry.
The degree of nonlinearity which each activation function can allow? Is there any difference?
Probably, but in practice, no.
What does it mean by that? Sorry.
So, just mathematically speaking, because all these functions look differently, you may think that value may not convey the same level of nonlinearity to the function. So that might be true, but in practice, actually, you don't have that problem because if you have more layers, then combining all of these value neurons at each node, and in the end, actually, you can represent whatever nonlinearity in your data without any problem. So my answer is where if we really would like to analyze the degree of nonlinearity, there may be some difference, but in practice, actually, you don't need to worry about that.
Okay, I got it. Thank you.
Any other questions? Okay, so let's move on to data preprocessing. So if we have infinite amount of data, then we actually don't need to do this. But we always have limited amount of data set collected, and that's usually very small, tiny amounts of samples among whatever all possible cases. For example, if we would like to learn something from the images, what would be the size of the all possible images in the world, which is uncountable. And what we have is just very, very tiny number of images, even if it's billions or trillions. So people use a lot of data processing or data augmentation to better use of those data sets. And here we are going to learn some basic skills we can apply for our data set. So, so record what happens. We use our images as is because all of those pixel values are positive, and we had some issues when we use some neural networks with sigmoid functions, or even though we can avoid that problem by using other activation functions like ReLU, still having all the positive values in the input is not a good thing. So what people usually do is zeroing out that effect by just translation. So suppose our input data is distributed like that. It's more like in the positive side of this axis and negative side of this axis. You take the average in each axis and you just add that to all the data points to move it to zero-centered. So on average, this data set is zero-centered. And if it is relatively more positive, then it will have positive values in the input. And if it's relatively negative, which means in our pixel cases, if it's relatively lighter, then it will have the positive values in the input. And if it's relatively dark, then it will be negative. In the raw data, everything is positive. But once we zero-center the data, that will change like that. And normalization is taken into different axes to remove the relative variance or importance of each dimension. So for example, in RGB case, in some domains, red components may be more important or has more variance, but than other colors like blue and green. Where let's think about some example. If you take some pictures from the ocean, that kind of data set will be all blue. So you may have less variance there, but you may have more variance in other colors. So it depends on your what problem you're going to solve. But in many cases, you actually have some benefits by normalizing the data to remove those relative variance in each input dimensions, because you don't know which one is more important. So you just remove it and just let the model to learn what is more important. So why do we do the zero centering? Here's another practical reason to do so. If you classify these using some zero-centered linear classification model, it actually becomes less sensitive when you zero-center the data. So suppose the data is originally located here. The x1 is always positive and x2 is always negative. When you have some linear classifier like that, if the slope slightly changes from green to orange, you have higher error rates than this one. When you zero-center the data set, it becomes more robust or less sensitive to outliers. So, and also it's easier to optimize because the input values of these data points becomes smaller in magnitude. So it becomes less sensitive to outliers and the parameters of our models. So just do the zero centering always. That's just the key message in these slides. And PCA and whitening, probably many of you already have learned and heard about this. What is PCA? PCA means principal component analysis. Given the data, and previously we just move it to just translate it to the center, but not just that. We here do axis alignment. So we actually to find the best coordinate system to preserve the variance of each dimensions and minimize the correlation between different axes. So it becomes like that. Actually rotate the axis to this way. And then when you whiten, which means you actually remove the relative importance of each dimensions, then it becomes like this, which looks like white noise. So we call it whitening. So let's see how we apply the principal component analysis. This part is a little bit mathematical. And if you are not familiar with some concepts, you may need to review some linear algebra stuff. But I will try to my best to explain this. First, you are given some data, x, and we do the zero centering, which is just applying this thing, just subtracting the mean of each directions, which you just translate it to the center. We just subtracting the mean of each dimensions like that. So we have x tilde, that will be our data set from now on. And compute the covariance matrix, which is defined as this. This is just mathematical definition of covariance matrix. Just compute that, taking the outer product of each of these vectors, and you're going to have this matrix. And then you perform eigenvalue decomposition. So if you're not familiar with this, it's not a topic that I can explain in 2 minutes, but here's my best. So from the definition of the eigenvalue decomposition, which looks like this, given this covariance matrix, we would like to align it to some other axis like that, which maximizes the variance of each, actually the first and to each axis. So you multiply some vector to that covariance matrix, and we would like to have it like this, which is this lambda is a diagonal matrix like this. And if you multiply some vector, which means that is kind of rotation, multiplying some vector or matrix, if you have multiple of them, this is rotation matrix to a new coordinate system like that. So suppose you rotate the entire coordinate system to like that, that's here. So that is determined by this matrix called U. And this U has to be orthogonal, which means each of these axes needs to be orthogonal to each other. So each of these columns of the U matrix is orthogonal to each other. So if you multiply U transpose and U, then it becomes the identity. So from the definition of this eigenvalue decomposition, you multiply U transpose to the right, then this will be just sigma, and to the right you will have the U transpose on the right side. So if you are not following this, it's okay. It's not you can learn within this class just in 5 minutes, but just try to remember that U is kind of rotation matrix, rotating the entire coordinate system of the covariance. And then the covariance matrix becomes diagonal. This part is important. So once you rotate the coordinate system, it becomes diagonal, and each of those variants axis-wise will be preserved, but all others will be just 0. Because we have the, by definition, this lambda, the diagonal matrix is like that. And we assume that these lambdas are sorted by its importance, its magnitude. So let's try my best to interpret this complex formula. Is given the covariance matrix from our data, we try to rotate it to make this results as much as diagonal like that. So all other these correlation becomes 0, and each of those coordinate, each of those axes, we have the variance represented here as lambda, and these are sorted by its magnitude. So lambda 1 is the largest, and lambda 2 is second largest, and so on. In the end, we have very small numbers because here lambda 1 is much larger than lambda 2, which corresponds to the length of this variance. And if you do that for high dimensional data, later you will have very, very small numbers. So you approximate this by setting all of these small numbers to 0. Then you can represent the data with much smaller number of dimensionalities, which is the k is much smaller than d. And if this is k is 2 or 3, then you can actually visualize the data set by preserving the variance as much as possible. If you don't understand this, it's okay. It's not your fault. PCA is one of the most widely used dimension reduction techniques in machine learning. And if you don't have background in the linear algebra, you may not understand what I'm saying now, but it's okay. And you can still use PCA because a lot of machine learning platforms actually provide the APIs for PCA. And if you just apply the PCA to some high dimensional data set and you cut off at some k of your choice, and then you will have reduced dimensions preserving the information in the data as much as possible. And you can just use it in many cases. But PCA is not widely used in raw pixels, but it's widely used in the feature space. And here are some examples. We are going to learn the details of these models in our lecture 8 later. But AlexNet, VGGNet, ResNet, all of these are really famous computer vision models, which was developed at the beginning of the deep learning era. And these are using some data pre-processing, like the mean, average, the average of the entire image or channel-wise. And in the video data set, they have used some PCA, which is less common, but they applied it in the feature space. So the main message of here is we do use a lot of data pre-processing, which is kind of simpler, like subtracting the mean of the image or channel-wise mean for each channel. And just keep that in mind that you can always use these techniques for your model. And if you don't know what to do with high-dimensional data, maybe just applying PCA can be a good choice as a beginning. So that's it. We have just 12 more minutes. Let's try to do this data augmentation part, which is easier to understand. What is data augmentation? So images we have are just the tiny subsamples of the reality, as I mentioned before. And there are lots of ways to just slightly modifying the image without affecting the semantics. So you may remember this figure from the previous lecture. But see here, this one is actually very different from this image. But as a human, we see that these two are almost identical. The only difference is it was shifted by 1 pixel, but we cannot recognize that as a big difference. So we would like to take full advantage of our existing data sets. And I'm going to show some examples of data augmentation, which you can obtain some additional data points, images for free. For example, like that. Suppose you have this cat in your data set, and your task is training some image recognition model from this kind of image. So once you have this kind of image as an input, then you have to output as a cat. But for human, we know that this one is also the same. This one is also cat. And we would like our model to output the same label, cat, once we have this input as well. But pixel-wise, as we said, these are completely different. So ideally, actually, if we can have infinite amount of data, we will have both of these in our data set. But because we have only this one, we create this one from this by reflecting. And we also feed this data to the model, which means here, we'd like to train our classifier to recognize both of these images in the same way. So we simply just teach twice. With this one, and this is cat. And with this one, this is also cat. So it will just learn from both of these images. So we just try to create a new image that we can teach, use a teaching material to our machine learning model. Horizontal flips makes more sense because of the gravity. Vertical flips sometimes make sense, sometimes not. Like this, this figure completely makes sense in our human sense, but this image maybe not. This is beach, but this is, yeah, it's still beach, but it's not real. So vertical flips sometimes make sense for some images, but not always. And random crops. So this entire image of cat is cat, but if we take only the this part of image, is it still cat? Right. So it should be still cat. So we crop just different part of the images, and we feed that as our training example. And we still know that this entire image is about a cat. So we can randomly crop different parts of the image, and actually we can use all of them as teaching materials. So 2 images with just a few pixels shifted should be similarly recognized. So not just few pixels, but we can just take randomly different parts of the image. Or scaling. So this cat can be captured in this resolution or this larger resolutions. So if we have this large data set, you can actually try to reduce the size of this image and capture the same size of the patch in different scales. So this cat's face may be captured like this size or this size or this size, and we would like to teach our model that all of these are cats, so you have to recognize this. If we just use this one, then this kind of scale only, then the model may learn that, okay, the cat's face should be in this size, and if it's smaller than that, it will not be able to capture it. So scaling is another thing. And okay, so continued. So random cross-term scaling, because we are trying to create more training examples by that, actually we can take advantage of the same techniques in test cases. So here's the common practice. For training, we pick some random error between the range. This is, you can actually forget about these exact numbers, but this is 256, and this is 480. So you may choose some random error in this range and takes the squared patch, which is the L by R, and you resize the image such that the shorter size to be R, and then actually you random crop 224 times 224 patch like that out of the resized images. So which means, given the image, you actually resize it to a small scale, where the larger side to be some number between these two, and then you apply some random crop of this size to have the different scale and different part within the input image, like randomly. And then for testing, you actually resize the image to 5 different scales, and then each size you can crop multiple patch of those image and classify them. Because our classifier is, we do our best to train our classifier to recognize the objects in different scales as much as possible and at different locations. But still, we may take advantage of these multiple scale images and multiple random cropped parts when we actually do the inference, and we may do some majority vote to what it is to just improve our performance as much as we can. So these are just practical matters. Let's try a little bit more complex data augmentation. Color jittering. You may remember when you take some photo, depending on the lights or the direction or many other factors actually affect how it actually looks like. So these are the same photo taken at the same place, but depending on the amount of lights when you actually, at the moment when you take the shot, it may look very different like that. So we'd like to make our model to be invariant to some slight lighting changes. We would like our model to output the same label cat for both of these kind of images. So we'd like to change the color slightly, but how? We don't want to randomly change the color of each pixels independently, then it will lose the shape. So one way I can propose is using some tools like this. This is the Microsoft Paint, which is the default software installed in your Windows. So, but you don't have to use this. We know that our images are usually represented as an RGB, which is the red components, green components, and blue components. But there are many other systems to represent colors, and one of them is this HSR, which uses 3 other different components: the color and saturation and lightness. So color is called hue. So what color types of that? And saturation means this direction, from more vivid to more gray. And lightness is on the right here. So it's most light is the white and the most dark is black, but in between we have these values. So for any RGB codes, actually you can convert it to this HSR in this MS Paint, but you don't have to use MS Paint, but you have these formula. So just following these formula, you can actually convert it any color to the HSL. So given the RGB, you compute these things, and hue, saturation, and lightness is computed using these formula. You can just code that in your program. And then you will have the HSL code for any given pixel. And then you add some noise. For example, reduce the lightness a little bit, or change the saturation, increase the saturation a little bit. Then you can make those pixels back to RGB using the same formula. So in that way, you can change the image of cat like that to this one, just by increasing lightness a little bit. So there are many other ways, but this is just an example of changing the color dithering. And in practice, there are tons of data augmentation techniques can be used. And I just gave some examples, but you can be creative to have more different data augmentation techniques, which is specialized for your problem or the task or the data set. Something like translation, rotations, or stretching, shearing, random blocking, adding noise, or mixing two images, adding a filter. There are a lot of filters actually you can apply. And this will be the first question of your homework too. So yeah, you will have some experience with data augmentation, which is really important in computer vision in your next homework. So today's lecture is done, and next time we are going to do the weight initialization and the second part of these practical issues in training the neural networks. So thanks for attending, and if you have any questions, please feel free to ask after this class, and you can actually ask in Korean after the class. Thanks.